Pig, Hive, and Jackal have much in common. They all translate high-level languages into MapReduce jobs so that the programmer can work at a higher level than he or she would when writing MapReduce jobs in Java or other lower-level languages supported by Hadoop using Hadoop streaming. The high-level languages offered by Pig, Hive, and Jackal let you write programs that are much smaller than the equivalent Java code. When you find that you need to work at a lower level to accomplish something these higher level languages do not support themselves, you have the option to extend these languages, often by writing user-defined functions in Java. Interoperability can work both ways, since programs written in these high-level languages can be embedded inside other languages as well. Finally, since all these technologies run on top of Hadoop, when they do so, they have the same limitations with respect to random reads and writes and low latency queries as Hadoop does. Now, let us examine what is unique about each technology, starting with Pig. Pig was developed at Yahoo Research around 2006 and moved into the Apache Software Foundation in 2007. Pig's language, called Pig Latin, is a data flow language. This is the kind of language in which you program by connecting things together. Pig can operate on complex data structures, even those that can have levels of nesting. Unlike SQL, Pig does not require that the data have a schema, so it is well suited to process unstructured data. However, Pig can still leverage the value of a schema if you choose to supply one. Like SQL, Pig Latin is relationally complete, which means that it at least is as powerful as relational algebra. Turing completeness requires looping constructs, an infinite memory model, and conditional constructs. Pig Latin is not Turing complete on its own, but is Turing complete when extended with user-defined functions. Hive is a technology developed at Facebook that turns Hadoop into a data warehouse complete with a dialect of SQL for querying. Being an SQL dialect, HQL is a declarative language. Unlike in Pig Latin, you do not specify the data flow, but instead describe the results you want, and Hive figures out how to build a data flow to achieve it. Also, unlike Pig, a schema is required, but you are not limited to one schema. Like Pig Latin and SQL, HQL, or HiveQL, on its own is a relationally complete language, but not a Turing complete language. It can be extended through UDFs just like Pig to be Turing complete. The final technology is Jackal. Jackal was developed at IBM. It is a data flow language like Pig Latin, but its native data structure format is JavaScript Object Notation, or JSON. Schemas are optional, and the Jackal language itself is Turing complete on its own without the need for extensions through UDFs. Let us examine Pig in detail. Pig consists of a language and an execution environment. The language is called Pig Latin. There are two choices of execution environments, a local environment and a distributed environment. A local environment is good for testing when you do not have a full distributed Hadoop environment deployed. You tell Pig to run in the local environment when you start Pig's command line interpreter by passing it the -x local option. You tell Pig to run in a distributed environment by passing -x MapReduce instead. Alternatively, you can start the Pig command line interpreter without any arguments, and it will start in the distributed environment. There are three ways to run Pig. You can run your Pig Latin code as a script just by passing the name of your script file to the Pig command. You can run it interactively through the grunt command line launched using Pig with no script argument. Finally, you can call into Pig from within Java using Pig's embedded form. As mentioned in the overview, Hive is a technology for turning Hadoop into a data warehouse complete with an SQL dialect for querying it. There are 3 ways to run Hive. You can run it interactively by launching the Hive shell using the Hive command with no arguments. You can run a Hive script by passing the -f option to the Hive command line along with the path of your script file. Finally, you can execute a Hive program as one command by passing the -e option to the Hive command followed by your Hive program in quotes. Jackal is a JSON-based query language that, like Pig Latin and HiveQL, translates into Hadoop MapReduce jobs. JSON is the data interchange standard that is human-readable like XML, but is designed to be lighter weight. You run Jackal programs using the Jackal shell. You start the Jackal shell using the Jackal shell command. If you pass it no arguments, you start it in interactive mode. If you pass the -b argument and the path to a file, you will execute the contents of that file as a Jackal script. Finally, if you pass the -e argument, the Jackal shell will execute the Jackal statement that follows the -e. There are 2 modes that the Jackal shell can run in. The first is cluster mode, specified with a -c argument. It uses your Hadoop cluster if you have one configured. The other option is mini cluster mode, which starts a mini cluster that is useful for quick tests. Next, let us look at moving data into Hadoop. We will begin by looking at Flume's architecture, then examine the 3 modes it can run in, followed by a look at the event data model. Flume is an open-source software program developed by Cloudera that acts as a service for aggregating and moving large amounts of data around a Hadoop cluster as the data is produced or shortly thereafter. Its primary use case is the gathering of log files from all machines in a cluster to persist them in a centralized store such as HDFS. Scoop is an open-source product designed to transfer data between relational database systems and Hadoop. It uses JDBC to access the relational systems. Scoop accesses the database in order to understand the schema of the data. It then generates a MapReduce application to import or export the data. When you use Scoop to import data into Hadoop, Scoop generates a Java class that encapsulates one row of the imported table. You have access to the source code for this generated class. This can allow you to quickly develop any other MapReduce applications that use the records that Scoop stored into HDFS. In Flume, you create data flows by building up chains of logical nodes and connecting them to sources and sinks. For example, say you wish to move data from an Apache access log into HDFS. You create a source by tailing access log and use a logical node to route this data to an HDFS sink. Most production Flume deployments have a 3-tier design. The agent tier consists of Flume agents co-located with the source of the data that is to be moved. The collector tier consists of perhaps multiple collectors, each of which collects data coming in from multiple agents and forwards it onto the storage tier, which may consist of a file system such as HDFS. Here's an example of such a design. Say we have 4 HTTP server nodes producing log files labeled httpd_logx, where x is a number between 1 and 4. Each of these HTTP server nodes has a Flume agent process running on it. There are two collector nodes. Collector 1 is configured to take the data from Agent 1 and Agent 2 and route it to HDFS. Collector 2 is configured to take the data from Agent 3 and Agent 4 and route it to HDFS. Having multiple collector processes allows one to increase the parallelism in which data flows into HDFS from the web servers. Oozie is an open source job control component used to manage Hadoop jobs. Oozie workflows are collections of actions arranged in a direct acyclic graph. There is a control dependency between actions in that a second action cannot run until the preceding action completes. For example, you have the capability of having one job execute only when a previous job completed successfully. You can specify that several jobs are permitted to execute in parallel, but a final job must wait to begin executing after all parallel jobs complete. Workflows are written in HPDL, an XML process definition language, and are stored in a file called workflow.xml. Each workflow action starts jobs in some remote system, and that remote system performs a callback to Oozie to notify that the action completed. The coordinator component can invoke workflows based upon a time interval, that is, for example, once every 15 minutes, or based upon the availability of specific data. It might also be necessary to connect workflow jobs that run regularly, but at different time intervals. For example, you may want the output of the last 4 jobs that run every 15 minutes to be the input to a job that runs every hour. A single workflow can invoke a single task or multiple tasks, either in sequence or based upon some control logic. This is the end of this unit and this course. As I said earlier, the components discussed in this unit have Big Data University courses that cover them in more detail. Thank you for attending. And here is a list of trademarks that may have been referenced in this unit.